As you go down the page on your syllabus, you see that yet before we even start to get into the details of absorption, we have another generality to cover. Very important generality dealing with ionization of drugs. If you remember, when we talked about solubility, we mentioned how you needed to have lipid solubility to go across membrane, but you also needed to have a certain degree of water solubility. One great event that occurs to drugs is that most of them are called weak acids or weak bases. A weak acid or a weak base is a chemical that exists in two shapes, two forms. A form that is referred to as being non-ionized, sometimes we simply say unionized. And when we say non-ionized, unionized, we mean it has no pluses, no minuses on it, no charges. And the other form is the ionized form. That would be a salt, which would have pluses or minuses as far as charges would go. Key point about being a weak acid or a weak base, you exist in a certain ratio of ionized and non-ionized. And you might think, well, what is going to be the relevance as far as the drug traveling in the body? The relevance is given to you on your screen right there. If a drug is ionized, it is water soluble. Think of salt. I'm sure you remember from high school, salt's formula, Na plus, Cl minus, and ACl as ions. Ions are water soluble. Certainly a drug that would be ionized therefore would have great degree of water solubility. In turn, what could that allow you to link to with pharmacokinetics? Any drug that would be water soluble is likely to be easily excreted. If you are trying to use your kidney and pee out a drug, certainly the more water soluble it would be, the easier the excretion or elimination of that drug. So you will associate ionization with water solubility and ease of excretion. Contrast the second point on the slide. When the same drug is seen as the non-ionized form, that non-ionized form is more lipid soluble. And lipid solubility certainly will help greatly to go across membranes, maybe to go across the blood-brain barrier. At the same time, being non-ionized and lipid soluble would not favor elimination at all. If the non-ionized fraction was to be filtered, you would imagine that it could very quickly be reabsorbed and stay in the body. Well, key points about drugs called weak acids or weak bases, they exist in a certain percentage of both forms, of ionized and non-ionized. What controls those fractions? It's the actual pH of the environment and the pK of that drug. I'm going to explain this to you in more details by using the board, and I will also refer to a number of points that we do review together when we see the biochemistry, and you'll recognize a lot of them from the chapter about enzyme kinetic in particular, where you'll see all the points applied to amino acids. A key issue is that the basic concept you see in biochemistry with amino acids and their pH and pK stories is we are going to generalize this for our drug. Let me wipe out the board. First point I would like you to think about is, what is a pH all about? Is it a constant? Is it a variable? pH is a variable. pH is a variable and it belongs to the medium. It belongs to biological fluid. For instance, we always think of the pH of the blood being around 7.4, or the pH of the stomach being around 1 or 2, depending on whether we have food, whether we started digestion, and so forth. pH is a variable. It's part of the body. pK belongs to chemicals, belong to the drug. And a pK is absolutely not variable. A pK is a constant. Two important individuals in the basics of pH and pK, called Henderson and Hasselbalch, looked at the relationship between pH and pK. And of course, linked to that pH and pK relationship, the percentage of ionized and non-ionized. Now, if I go to the next slide on your screen, you would see that there are two types of drugs, the weak acids and the weak bases. And we need to understand those fairly well to have an idea how pH and pK can change the form. If we first work with weak acid, you see that weak acids have two types of structures. The first one to the left is R, whatever that might be, COOH. Notice, when you write it COOH, there are no pluses, no minuses. This is the unionized form of that drug, and it can cross membrane. It is more lipid soluble. But that unionized form is in equilibrium to the right with RCO minus. Minus means it's ionized, it has a charge, and therefore it would be better cleared. It's the form that we would eliminate. When do you see the drug weak acids mainly as COOH, lipid soluble? When do you see it mainly as CO minus, water soluble and better cleared? It all depends on the pH of the medium and the pK of the environment. Let's go back to the board. If I call WA a weak acid, and if I write down the fact that it exists as COOH or COO minus, tell me a little bit about an acid medium. An acid medium is a medium that has a low pH. Now, you remember an acid medium, for instance, in chemistry, we like to think of it as a pH less than 7. Now, that's great when you look at water and how it handles that little H that we see on the molecule here. However, when you work with the body, you think, well, you know, the real neutral pH is 7.4 or so in the blood, and we like to call acidosis in physiopath less than 7.42 and alkalosis more than 7.42. Where are those numbers coming from? They're really coming from the pK of the actual drug, and your best bet would be to think of the drug based on its pK. Think of pK as being simply a value like 7. Anytime the pH will be below the pK, the medium will be acidic. So I will call an acid medium a pH that is below the pK of the chemical, whatever that pK might be. For instance, if the pK is 2 for an acid group, then a pH of 1 would be below it, and the medium would be considered acidic. If the pK is greater than 2, maybe 3 or 4, well, that would be called a basic medium. And a basic medium, therefore, I'm going to call it basic M, would be when pH is greater than the pK. It so happens that the pK of water is 7, and now you understand where an acid medium being pH less than 7 comes from, or a basic medium being pH more than 7 comes from. It comes from environments that are mainly rich in water. Here we want to apply it to the drug. Second point, and let me use a different color for this. You know that chemically speaking, when a medium is acidic, it has a lot of protons. Plenty of protons, H pluses. When a medium is basic in chemistry, it has very little protons. So now just put the two things together. If you look at the two shapes of the drug, COOH or CO minus, when are you more likely to see a proton attached to the drug? When they're plentiful in the medium, or where you don't find them? Obviously, it is when you're going to have plenty of protons in that medium that you'll find it attached to the drug. And therefore, the COOH shape of a weak acid is found mainly in acid medium. Mainly when the pH is below the pK of that drug. Contrast, when the medium is poor in protons, the drug simply will not have a proton attached to it. And for a weak acid, it means it's going to look like CO minus. Notice there's no more protons attached to the drug. Of course, it now means that in a basic medium, when pH is greater than the pK, my weak acid is now ionized. So if you go back to your slide, you see that where we said weak acid crosses membrane on the left as RCOH, tell me, what must the medium be like for the drug that's called a weak acid to cross that membrane? Hopefully you're telling yourself, and myself too, although I can't hear you, that it's an acidic medium that will allow the drug to be mainly unionized as a COH form. On your right hand side, RCO minus is the form that has lost its proton, And that will occur mainly when pH is greater than the pK, when the medium is alkaline basic. Now this holds for weak acids. There's a second group of drug that we need to work with, which are weak bases. Weak bases, on your diagram, you see them as having, for instance, an amino group. And amino groups, just like acidic groups, tend to exist in two forms. To your left, you see an amino group called NH3+. To the right, you see it, NH2. Which one do you think has grabbed a proton? The one called NH3+ on the left, or the one called NH2 on the right? Logic would be the one called NH3+ has an extra proton attached to it. The one called NH2 does not have that proton. It lost it. Do you remember when we have plenty of protons? If you look back at your board, you remember it's in an acid medium, when pH is less than the pK of the drug, that there are plenty of protons. So tell me, when would the weak base be mainly ionized? A weak base is ionized on the left of your diagram, RNH3+, when protons are plentiful, which is in an acidic medium. A weak base will be unionized in a basic medium when there are far less protons in solutions. Well, that's to try and understand the actual chemistry and how it happens. But you know, some of us hate chemistry, and that's why we're in medicine. And if you want to summarize this and just use words, I often love to do that. Well, just using words, think of the name of the drug and the name of the medium. If the name of the drug and the name of the medium match, the drug is mainly unionized. Look, the weak acid. If a weak acid is in acid medium, the two names are the same, weak acid and acid medium. It is COOH. It is unionized. Bottom line, weak base in basic medium, the two names are the same. You have RNH2. It is unionized. When the names are identical, drugs will cross membrane, will be unionized. Contrast, when the name of the drug clashes with the name of the medium, a weak acid in basic condition or a weak base in acidic condition, the names are different. Then in that situation, the drug will be mainly ionized and more water soluble. For instance, a weak acid in basic medium would be CO-, which is better cleared. A weak base in acidic medium would be NH3+, which is ionized and better cleared also. To finalize this, you have a diagram at the bottom of your page called ionization, and that diagram tries to represent the behavior of weak acid and weak bases as we change the pH. So first, let's look at the axes of that diagram. If you look at the bottom axis looks at pH minus pK as a value. When pH minus pK is 0, for example, then the pH equals the pK. So when pH minus pK on the left of the diagram is a negative number, it must mean that pH is less than the pK. And when pH is less than the pK, we know that the medium is acidic, or that there are plenty of protons. The left of the diagram therefore shows you the drug in an acidic medium. To the right of that axis, pH minus pK is a positive number. When pH minus pK is a positive number, it means pH is greater than the pK value. When pH is greater than the pK value, obviously the medium is basic, and a basic medium would be a medium that is pretty much devoid of protons. The drugs will lose their protons. Look now at the left y-axis of that diagram. The left y-axis shows the percent non-ionized. Percent non-ionized refers to the percent of the drug that would have no pluses, no minuses. You know, for instance, for a weak acid, it would be COOH, or for a weak base, it would be an H2. As you go up on this axis, you increase the fraction of the drug that would be non-ionized. The axis to the far right of that diagram shows you renal clearance of the drug, and notice the orientation of the axis, it goes downward, meaning your renal clearance increases the lower you are on that axis on the diagram. What could you associate with renal clearance? You know, being eliminated. Ionized or unionized? I hope you were thinking ionized. An ionized drug, the more ionized they would be, the better cleared that drug would be. Obviously, the axis goes in the opposite direction than the unionized axis on the left of the diagram. Let's look at the black curve. If you look at the black curve, you look here to the top left corner of the diagram at a drug that is mainly non-ionized in an acidic medium. For drugs to be mainly non-ionized, the name of the medium and the name of the drug must be the same. So it must be a weak acid in an acidic medium. And what happens to the weak acid in acidic medium? As you go to the right of the diagram, the medium becomes more and more basic, and the drug becomes less and less unionized, to the extent that to the bottom right of the diagram, that weak acidic drug is now very well cleared, because it is no longer non-ionized, rather it is ionized and water-soluble. Weak acids in basic medium to the right of your diagram are well cleared, not well absorbed. Weak acid in acidic medium are mainly unionized and would be very well absorbed but poorly cleared. Conversely, the light shaded curve shows you the behavior of a weak base as you change the pH. On the bottom left of the diagram, you see that weak base in acidic medium. The name of the medium, the name of the drug are opposing each other. The drug is mainly ionized and very well cleared. Very little of the drug, therefore, is in the non-ionized form. There would not be a good absorption of that drug, just a good elimination. Contrast, as you go to the right of that diagram, you notice that the weak base is becoming more and more non-ionized the more basic the condition become. Of course, this decreases its renal clearance, but it improves greatly its permeation across membranes. Well, let's put this in words if you want. You know that the key issue for us would be that ionization increases renal clearance of drug, and when we think of this, there is a great way then of trying to speed up elimination of drug. All we need to do clinically is to change the pH of a medium to favor the ionized fraction of that chemical. Now, when that chemical reaches the kidney at the level of a glomerulus, you keep in mind that only a free drug would be filtered. Free meaning unbound from proteins. When is it pathologically that you lose proteins? You're thinking nephrotic syndromes. If you have a nephrotic syndrome like a membranous glomerulopathy, or you're a diabetic with Kimmel-Steele-Wilson's disease, in that situation you may lose protein-bound drug. But in any normal kidney, only free drug is small enough to be filtered. Once filtered, we know that the non-ionized form is quite likely to go back across the membrane and be reabsorbed and stay in the body. It is mainly the ionized fraction that will tend to be trapped into the filtrate and be eliminated. Well, what should I do to a weak base to enhance its ionization? To enhance the ionization of a weak base, I want it to be in its opposite medium, an acidic medium. An acidification of the urine will increase the ionized fraction of weak bases and enhance their renal elimination. In the margin of your syllabus, you'll find a little note that will tell you how you can acidify the urine or alkalinize the urine. To acidify the urine, something that people who have issues with gout know very well, is the use of cranberry juice. If you drink cranberry juice, your urine becomes fairly acidic, and the more acidic that urine, the more likely weak bases would be easily eliminated. But what do you think would happen to a weak acid such as uric acid? Uric acid, as a weak acid, if you put it in an acidic medium, the names are the same. It'll be mainly unionized and less water soluble. That's why if you drink cranberry juice and you have gout, you're quite likely to form urate stones and then end up having some issues with kidney function, maybe hydronephrosis. Who knows what kind of nasty scenario would happen. Contrast, at the bottom of your slide, you see alkalinization of urine would enhance the excretion of weak acids. And weak acids, by far, are the most common form of drugs that will be administered. If you take a drug orally, the first medium that drug will get into is the acidic medium of the stomach. And in an acidic medium of a stomach, if you give a weak acid drug, you'll have mainly unionized form of the drug, which is easily absorbed. That's why on your exam, if you were dealing with pH/pK question and they weren't telling you whether the drug is a weak acid or a weak base, your best bet for generality is to think of the drug as a weak acid drug, in which case acidic medium would enhance the absorption, basic condition would enhance the elimination. To summarize all these points, you have a figure illustrating the renal clearance of a drug. In this figure, you see the glomerulus to the left, and you encounter the free drug unbound to protein reaching the glomerulus. The free drug is either ionized, letter I, or unionized, letter U. Both ionized and unionized drugs are shown to you on the diagram as being freely filtered, providing they're not bound to proteins such as albumin. Once in the proximal tubule to the right-hand side of your diagram, the ionized fraction is trapped in the filtrate and excreted. The unionized fraction is shown to you as being reabsorbed into the blood vessel. So play again with pH with this, and let me ask you, if I was telling you that quinidine is a weak base, under which condition would quinidine be better eliminated? Quinidine is a weak base. You remember that basic drugs will be mainly ionized in an acidic medium when the names are clashing. And if I have very acidic urine, quinidine will be more ionized and better excreted. Vice versa, if I was asking you when is it that quinidine would be mainly unionized and reabsorbed? Unionized would occur when the medium is more basic for that weak base, and reabsorption of quinidine is more likely the more alkaline the urine would be. Or if you want, just for the heck of it, let's link it to a bug infection that you would see in micro. You remember bacteria that can alkalinize the urine? Hopefully you're thinking of bacteria like Proteus, bacteria like ureaplasma, and those urease producing type of bugs tend to cause an alkaline medium. So imagine a stem right now with a Proteus infection asking you about what would happen to elimination of that drug quinidine, knowing that quinidine is a weak base. Now you have an integrated board question that deals with pH/pK, a drug, and an actual infection that could be described to you as a stem. Let me give you the answer though. Obviously, if you have a Proteus infection and your urine is basic, a drug such as quinidine would be more unionized and better reabsorbed. This closes our general principles section of the general principles, essentially telling you about pharmacokinetic being 4 phases: absorption, distribution, metabolism, and elimination. The roles, of course, of solubility in lipids to permeate membrane, the surface area, the vascularity to increase diffusion across membrane, and the fact that drugs go down concentration gradients. And finally, the complexity of pH/pK issues, allowing the drug to be ionized to make it water soluble or unionized to make it more lipid soluble.